Good morning, everyone. So the next assignment, which was just posted, is homework 6. And for this assignment, you get a slightly different robot in the gazebo simulation. And what you're supposed to do with the robot is map out the maze that the robot is starting in. This is in preparation for the next assignment, where you'll be taking the control program that does mapping, that you'll be building in this assignment, and then doing pathfinding on the map to get to the goal, get to the end of the maze, which is just the goal from the previous assignments. So, I want to talk a little bit about how to do mapping on a robot, and specifically how the robot that you get for homework 6 works in such a way that it's useful to do mapping on it. So the robot that you get has a couple more sensors than before. Specifically, you get a robot, so here's your robot, and this is a LiDAR on it, like the homework 1 robot does. And this LiDAR is going to shoot out 7 lasers. We could have done 8 lasers, but this robot can't see directly behind it, which is fine. Just be careful if you're driving backwards, because you might bump into stuff. But, so this has laser sensors forward, 45 degrees left and right, directly left and right, and then 45 degrees back. And these will give you the distance to any obstacles like a wall that might be in the way. So if there's a wall there and a wall there, then this sensor and that sensor are going to give us hits, and maybe this sensor and this sensor are not able to see far enough to see the wall. I think the laser sensor is set up so that it only sees 2 meters, which is really short for a laser sensor, but it's fine for this example. Now, the other thing that we have in addition to these laser sensors that let us detect obstacles is we have some pose information. And it's the same sort of pose information that we had in homework 1. We have X, we have Y, and we have theta, or our angle. But these are now inaccurate sensor data. They are designed to drift. So over time, if you're just sitting still, the robot will see its pose change slightly. And additionally, they have another error in them. And the result is that the X and Y can be as much as like a meter wrong, and the angle can be not hugely wrong, but if you think you're facing exactly forward, you could really be facing 15 degrees off or something. So we have our laser rangefinder, and we have some pose data. We have the same sort of actuators as in the last assignment. We have sort of tank drive wheels, although it looks a little bit more like tank treads this time. And the tank tread wheels, we can say how fast we want the left side to go and how fast we want the right side to go. And those, again, are going to be slightly imprecise. If we tell it to go exactly like 2 forward on the left and 1 forward on the right, we may get 1.8 on the left and 1.1 on the right, just to make it so that we're a little bit more realistic as far as what robots are going to do. Robots don't do exactly what you tell them to, and if you want them to, you're going to have to take advantage of your sensor information to see what the robot actually did, and then correct your commands to try to get it to do better. All right, so we have laser, pose, we have motion, and that's pretty much the whole story. That's what we've got. And then we have this thing in a maze layout that has some of the same properties as the maze layouts that we had before, although not every wall is a right angle, and there's no rule about where the walls are, so we can't take advantage of sort of the structure of the environment to just like figure out what row we're on. We could still use some of the strategies from the previous assignment, but instead I want to do it the sort of the more ambitious way. We're going to build a map. And so the standard method, or a common method for building a map in this sort of robotic situation, is that we start out by allocating a map in memory, and then we fill in the map as the robot drives around, and we find out what's going on. And the way we're going to represent this map is as a grid. So So we make this big map, and we can think of it sort of like a chessboard or something. Now, that's not quite high enough resolution to be useful, but as the robot's driving around, we try to figure out where the robot is. We have some pose information. So if the robot is here on the map, then maybe when we get these laser hits, we can figure out that if we take the position of the robot, the direction of that laser scan, we have distance and angle for each laser hit, and we apply it on the map, we may figure out that the laser hit that we saw there is this square on the map. What we're going to do is we're going to fill in that square and say there's an obstacle there. And we might say that this hit over here is this square on the map, and we'll fill in this square and say that there's a laser hit here. So that's the basic idea of occupancy grid mapping. Now we want the grid to be high enough resolution that we can like usefully represent the environment, but it doesn't have to be super high resolution. We're dealing with a robot like this, where the robot itself is like 0.5 meters, and the like obstacles that we're dealing with are like 1 meter. Then what I'd start with, just playing around for a grid resolution, is a 0.25 meter grid resolution. All right, so every time we have the robot driving around, we have this grid overlaid on the map. I'm just going to draw it directly on over the robot. And the grid isn't necessarily going to line up with anything. But as we're driving around, we're getting this information from the laser scanner about whether or not there are obstacles in grid cells. So for example, we have this laser facing forward on the robot, says that there's a hit here. So we can say that this grid cell is occupied. There's an obstacle in that grid cell. But we also now have evidence that this grid cell here is not occupied because the laser passed through that grid cell and didn't hit anything. And so that's what we're going to do. So we might end up with some sort of, well, the thing that we want to end up with is some sort of representation of how convinced we are that each grid cell is occupied. So maybe we say that we had a hit here, and we're going to decide that now we think that there is a 75% chance of this being occupied and a 25% chance of this being occupied. And if you remember your Bayesian statistics, you can go ahead and use the formula for updating knowledge based on new information and try to apply that here. But probably the laziest thing to do is just for every cell, we keep a count of two fields, which is hits and misses. We start them out both at 0, and then when we have a hit in a cell, we increment hits. When we have a miss in the cell, we increment misses. And then when we need to then determine if the cell is occupied or not, we write some function of hits and misses that will then allow us to determine how we want to treat this cell. And we may treat it as being probabilistically full or completely full. So for example, we could say full if hits is greater than misses. I don't know if that's a good answer, but that's the sort of idea that we could deal with. So the starter code for homework 6 has the robot sort of driving around. I didn't actually run it for very long to see what it does. It might wall follow, it might get stuck somewhere, but you want to try to update that control, that like driving code, to try to get the robot to drive around as much of the map as possible without getting too complicated. And then as the robot's driving around, we're going to get more and more evidence about which cells in our grid are occupied and which aren't. We get to fill them in, and will result in having this map. There's a couple of other interesting things that are going on. We don't know our exact position, we don't know our exact angle, so as we plot out from where we think our robot is and where we think the laser hit and what angle we think the robot's at, sometimes we're going to like plot this out and end up in the cell that we're supposed to, and sometimes we plot this out and end up in the wrong cell just because our information was wrong. And so it's possible that we'll just generate completely wrong information just because we happen to get a bad combination of stuff. So another thing that's useful to do in this sort of high uncertainty mapping situation is after a certain amount of time, we might want to have our cells decay. So if we haven't updated a cell in 60 seconds, then maybe it's time, and I think time is actually one of the sensors we have on our robot here. You'll have to go look at the robot.hh interface, but I think time is one of our sensors. So you want to keep an eye on when cells were updated, and if a cell is really old, it might be worth making it decay in order to try to get a better idea of what's on the map. On the other hand, if we're trying to make a map, maybe we don't want to have it decay. That's something to play with. The thing that we're going to be doing in homework 7, which is the sort of goal of this map, is once we have a map where we've like filled in all of our cells and have some idea what we're doing, and we want to go to a goal, let's say our goal is over there, we want to then be able to run a search algorithm, a graph search algorithm, which ends up being a good map search algorithm, like A star, in order to try to find a path over to the goal. And if we had misidentified a doorway in our maze as being a wall just because we got a bad piece of sensor data, we want to have some chance of not just having forever marked that doorway as being a wall. We want to be able to eventually like figure out that that was wrong, go look there again, and get the correct information. But we don't have to worry about that particular problem too much until homework 7, which is next week when I'll talk more about A star. I've posted a couple YouTube videos that cover this idea from a little bit different angle. That should help. But really the goal in this assignment, or the plan on this assignment, is to go take a look at the starter code, come up with a data representation for this occupancy grid thing here. We're in C++, so here's a recommended idea. You can do a vector of cell, where cell is some new data type. Another option is you could do a map of pair int to cell, which has an advantage if you don't know how big your map is. But you want to come up with some data representation like this for a occupancy grid map, and you want to go ahead and modify the starter code to fill it in. So yeah, good luck on the assignment, and I'll see you in lecture.